So what you're about to see is based upon my experience in concrete. And a lot of that experience has led me to believe that steel is a great construction material. The background, well, coming from the UK, precast concrete panel buildings were very popular in Britain in the 1950s and 1960s. These were built very quickly and very cheaply to replace the slums that had been bombed out, basically, during the Second World War. And they even called it the system build, residential towers. And then we had that, Ronan Point, 1968. This was a system built precast concrete tower block, and something went wrong. Basically, somebody lit a gas heater, which blew up and knocked out one of the panels, causing disproportionate collapse and progressive collapse of this tower. This I discussed in seminar number 3, Learning from Failure. That seminar was recorded, so if you're on YouTube, you can go look that up. And again, if you're watching this on YouTube, then leave a like and subscribe to the channel, share it with your friends, and comments and questions can be left within the comments section below. So this incident pretty much killed the high-rise precast concrete sector. And precast has changed quite dramatically since then. However, in New Zealand, we love precast concrete. So we'll look primarily at the New Zealand experience of precast concrete and how we do it here. And we'll begin with some examples of precast concrete construction, some nice pretty pictures, a brief mention on the design, some aspects which are specific to precast concrete as opposed to in situ, things like handling and demoulding and transport and so on. We'll look at the shop drawing production, how we produce drawings that need to be used by the precaster. Look at some of the issues with connections, weather tightness and so on, how you get those joints together. There's an awful lot of cast inserts to think about. And maybe the issue of bend out bars. We'll go into detail about the kind of finishes that we use on precast concrete, which is the unformed and the formed surface finish, and there's codes for those. We'll look at the codes for placement and erection, transport and demoulding as well. And a brief word upon progressive collapse, disproportionate collapse as well. So here are a few examples of precast concrete, and it can produce quite a nice building very, very quickly. And this is probably a better example than my experience has come across, because you can have a full height panel. Basically, the height of the panel is the height of the building. Here is slightly more complicated. You're into 2 stories. Try not to look too closely at this picture because you'll see many safety transgressions. Again, that is an issue with precast concrete construction. Is safety seems to be a secondary concern as to how you land these things, how you place them safely. The chap in the standing on the beam, putting his hands on the precast unit, I wouldn't recommend that. And some more examples. And one panel lifted into place. You could even do an entire house out of precast concrete panels. Personally speaking, I don't particularly like it because it's got that industrial look, and I prefer a much more homely look for my houses. You can get some quite dramatic effects if you put the effort in. So to get the surface finish of a high quality, it demands an awful lot of attention to detail, and particularly in the transport and erection process. So somebody asked about the design. Well, it's reinforced concrete. So NZS 3101, that's the concrete standard you need. So pretty much all the clauses in 3101 apply to precast concrete, but with some special attention to clause 18, which discusses precast concrete and composite flexible members. When they talk about composite, they're talking about precast plus cast in place, not steel and concrete. There's also 9 for pre-stressed, and it goes on to post-tension. I'd advise you as an ordinary structural engineer to stay away from that because that's a specialist skill. And the best people to design your pre-stressed concrete are the people producing it, and they will normally have a team of engineers. Part of that is the pre-stressing is dependent upon their setup, how they like to put their tendons and how much stress they can put into their tendons as well. Appendix B of 3101 talks about the special seismic design of ductile jointed precast concrete structural systems. So, coming to design considerations, as always, you're designing for the final situation. And if it's just in situ concrete, that's your only design stage. That's your only situation you're designing for. However, for precast concrete, you need to think about the demoulding and lifting stage. You need to think about the transport stage, the construction or temporary condition. So your panel will be cast, demolded, transported and lifted into position. And all of those will put different levels of stress, different actions upon that panel. And also helps them think about how the temporary works are going to be made, because if you put panels in, they will need propping. So here's an example of a casting bed, which is a fairly typical arrangement for the precasters I've seen here in New Zealand, and quite similar to the ones in the UK too. You've basically got a steel casting bed, and that's heated. So you basically have a warm floor. The point of the heating, of course, is to accelerate the curing of the concrete of the panel. So they are laid on their back. So this is a wall panel they're producing here, and it's cast on its back, hence the expression tilt panels. Because once upon a time, they used to actually make these on site, large panels cast, and then just tilt them up into position. Generally, they tend not to be cast on site these days. Examples that we need in joining these panels together. So you're looking at the bottom of the panel here. This is a wall panel, and we have these things called Drossbach ducts. So these are basically thin metal tubes, and the starter bar from the previous panel comes into here, and we grout that up. Bear in mind, this is quite thin, so don't walk on it if you're inspecting it, and it needs to be protected. These can be quite easily damaged during the casting process if not looked after. We need to lift the panel out of its demold and use these lifters to place it in position, and we call them lifters. Here's an example of a typical lifter at the top of a panel. In this case, they've added extra rebar to distribute the lifting force. An alternative to Drossbachs are grout sleeves, and these are much smaller, and they rely on the epoxy that you put in them to make the bond between the reed bar and the reed grout sleeve. Personally, I don't like them because they don't give you enough tolerance. So in this case, you've got a tube, a sleeve that's 32 millimeters internal diameter, into which you're putting a 16 millimeter bar. That only gives you 8 millimeters on either side. That is a tiny amount for construction tolerance. Whereas your Drossbach, you're normally looking at a 50 mil Drossbach for a 20 mil bar. That gives you a bit more space. It's also threaded inserts, so if you want to connect other walls in the perpendicular direction, you can connect the starter bars to these things. These are threaded inside, and you cast them into the panel at the time of construction. So in terms of design, when you're designing these lifters, you need to take into account how the panel is lifted and how the slings are met. So there's a little diagram they give you in the lifting design manual. And the tighter the rope, as it were, or the bigger the slinging angle, the bigger the load. So ideally, you want to be above that 60 degree, sort of below the 60 degree mark in there. The design lifting manual will give you these little diagrams as to how to calculate the forces in your cables. The interesting point here, even if you've got 4 lifters, you've got to allow for the fact that 2 of these ropes could be slack. So therefore the load is only ever taken by 2. If you've got a lifting bar or a spreader, you can potentially spread it among all of the lifting positions. There are a number of factors to take into account when calculating the lifting force that you need to allow for. Not just the panel weight, but obviously the adhesion force of lifting it out of the mold, and the demoulding factor, the sling factor, and the dynamic factor where applicable. So if you jerk the chain, as it were, when you're lifting it out, that will increase the lifting force that's imposed upon your lifter. And don't forget, these things are cast flat, so something that's going to be taking vertical load, pretty much vertical load only in the permanent condition, is now taking a bending moment as you pull it out. The bending moment is down to its self-weight. Here are a couple of examples of the lifters. The one on the left is a short one and must be used with additional bent bars to spread the lifting load. The one on the right is a hair clip or a hairpin, and that doesn't necessarily need additional steel to spread the load. And you'll see there's a big hole on the top, which this clutch then engages with it, and that's what you tie onto your crane. The clutch has got this mechanism which will allow you to release it remotely by tying a rope on the bottom of it. Here is a spacer or a packer, so when it's being cast, you put this in and then you can pull it out to reveal this opening as well. How do you connect the panels? Well, we have a range of systems. Most of these come from Reed. And if you're looking at doing precast concrete, you can't ignore Reed. In fact, it's pretty much essential that you get hold of as much information as you can from Reed. They make couplers and they make threaded inserts to connect your bars. They are threaded inside with the thread that goes with a Reed bar as well. The alternative, if you want metric ones, they do metric threaded inserts, like the one shown on the bottom there, and you can bolt a metric bolt into it. But you do need some clever detailing in there. So here's some examples of how the Drossbachs would go in, and the lower panel starter bars come up and into the Drossbachs, and then we pour grout. You pump the grout in from the bottom hole and it squirts out of the top. Here are the grout sleeves I mentioned before. Again, these are relying on using effectively an adhesive, a Ramset Epcon C8 in this case, to provide your continuity between one panel and the next. Yeah, we'll come back to that. Shop drawings. Here's an example of a typical shop drawing for a precast panel. And you want to show as much detail as you can, well, all the details you need to build it. So that's all the rebar, the sizes, the numbers, the spacing, and any cast inserts, any parts that you need blocking out, and any parts that need retarder put on them to make the joint. Here's another example. So we've got additional bars around the Drossbachs. So you'll see these extra links. You zoom in on that. And again, some more typical examples of reed bars. Here's showing the lifters. You need to show the lifters in the panel as well, and any additional rebars you need. You need to show any rebates and chamfers that the panel has to have. Here's an example from my own project here. This is a relatively simple example of a wall panel. And this came on 2 sheets. And here's that one that we prepared earlier with our nice Redco logo on it. A nice simple panel. And here's one that's not so simple. And it was insistence of the precast to have everything on one drawing. Now, you need to talk to the precaster because that isn't always the rule. The latest precaster is quite happy to put things on several drawings as well. And this panel was so complicated, and we'll see what happened to that in the next session in 2 weeks' time. There was so much rebar, I ended up splitting it into horizontal and vertical reinforcement. And yes, it was as complicated as it looks. The important information is down on the right-hand side. So you need to tell the precaster, or the precaster needs to work out the volume and the weight in particular of the panel, what grade of the concrete, what the finishes are, and here what are the codes for demoulding, lifting and placement. So let's look at those in a bit more detail. So here are the demoulding options, and it really depends how many lifters you put on your panel, and that will depend on the shape, size and weight of your panel. Simplest one, of course, is just lift it up with the 2 hooks. So that's D1 until you get to much more massive panels where you have multiple spreaders and multiple lifters. You can combine face lifters with edge lifters as well. So loading, so you've pulled it out of the mold and you can load it into storage or load it onto the truck. And again, these are the lifting options, simplest being L1. But to spread the load, it's usually better to use a spreader beam or a lifting beam. Go for L2. Transport options, and again, this is down to the precaster. So they will usually choose the style of transport and what they need to do it. And if you're putting them flat on a truck and driving over the roads of New Zealand, your panels will break. You need to use timber dunnage underneath it so that you spread the load and secure the load so it doesn't bounce around. More often than not, it'll come on a specialist truck, and the panels, wall panels in particular, will come vertically. Placing options, there seems to be more placing options than lifting and demoulding. So you can use the combination of the face lifters with the top lifters as well. All of these codes, by the way, are available on the New Zealand Precasting Association's website if you delve deep enough into it. Now, you also need to specify the surface finishes. So you have 2 surfaces, one MS mold face, and then you have the F classes for how you want that finished. Generally, you'll be looking at an F3 or an F4 for most of your wall panels. You also have an unformed finish, also known as the trowel face, sometimes known as the near face as well. And there's a range of codes you can use with those. Again, you're probably using, for most walls, U3 and U4. But these codes are not just for precast concrete, they're also for in situ and things like roads and warehouse floors. So you have textured and grooved and scabbled finishes as well, or even a ground finish. So these codes are again available on the New Zealand Precast Association's website. So what do we do about the shop drawings? Normally, your precast concrete subcontractor will be doing the shop drawings, and that would be the ideal situation. Unfortunately, that doesn't always work, and they do not have sufficient technical staff to do the shop drawings. But the shop drawings follow the same procedures as you do shop drawings for any other component in a building. So you'll have steel contractors producing steel shop drawings. You may have a temporary works contractor that produce the propping diagrams and the scaffolding diagrams and calculations to go with that. So as a structural engineer, you'll be passing your structural engineering drawings, usually through the prime contractor, and they will pass it on to their subcontractors. The whole process goes through reviews and markups. So let's look at that in a bit more detail for the precast concrete shop drawing production. You, as a structural engineer, you produce your structural drawings, you can pass those to the precast contractor, and they prepare their shop drawings. They should do an internal technical review. Once they're happy with that, they submit them back to you for review. If they're okay, you can sign them off and they go off into production. If they're not okay, you mark them up and send them back for revision as well. And the more complicated your building is, the more complicated your panels will be, and the more times you'll go around that loop. So what are the design issues? Well, as we found out at Ronan Point, robustness. It's very difficult to make a multi-story precast concrete building inherently robust. You have to go through an awful lot of effort to tie everything together. And if you do that, you will avoid a progressive collapse because you need to provide alternative load paths. How do you join the panels, and particularly if it's precast panel to another precast panel? How do you make them weathertight? So you've got lots of joints in your building now, and you need to join them and seal them, keep them weathertight, keep the water out. Shop drawing production can be a much bigger job than is anticipated as well. Don't forget, you need to detail the casting inserts or any bend out bars, so you can put bars in the panel to be bent out on site to make the connections. The shop drawing should show the lifters and the process for demoulding, transportation, placement and erection. All of these are design considerations. So when you're designing your precast concrete building, you need to have a good idea how it's going to be built. And probably the worst thing you can do is design the whole thing to be in situ and then at the last minute decide we're going to do it all in precast concrete. You then do this mad scramble as making the thing work and how to join it all together. That is not a very elegant solution. You also need to consider the surface finishes that you'll specify. So here is a typical joint. It's the vertical joint between two panels, and so you leave a little bit out at the end of each panel. It's shown here and here. And you cast an in situ bit with extra lap bars. This is taken from the Precast Concrete Design Manual. I'll give the reference at the end. Here is one for a larger panel which is sat on a foundation. So you put in your foundation, you cast up to the base, drop your panel in, then put your dowel bars in, and then cast the rest of the foundation around it. So you need to tie in the bottom of your panel into the rest of the structure. Here are a couple of examples of how you do an external joint. I don't particularly like these joints because they do end up being very vulnerable. You see, you have these little bits here that have no reinforcement in, and it's very easy to break them off in transport or erection. So the one on the left is the Grout Sleeve version, and the one on the right is the Drossbachs version. So these both provide the continuity between the panels above and below, as it were. And it's a good idea to tie in your panels into your slab, where you'll get a more robust building. Notice that the joint here is at the floor level as well. I'm presuming they've put this step down in the theory that it's going to keep the water out. Now that's the theory. If you seal it properly, it will keep the water out, and I personally think it would be much better detail if you just put a chamfer in there and seal it, because what you're doing here is adding more complications. And yes, there are cases, and we've got them on our site, where we've got 2 layers of these grout sleeves. If you've got 2 layers of reinforcement and you need to put 2 layers of reinforcement in at the joints between your panels vertically, then your walls are too thin, I would say, and you need to think about redesigning your building. So, what are the secrets to successful precast concrete construction? Well, these are my hints and tips, copyright me, but they should be fairly obvious, I would hope, to most people. First of all, choose a competent design consultant. So this is aimed at the client. And if contract picks a consultant who doesn't know anything about precast concrete construction, they're going to head into trouble. So you want a professional consultant who knows about precast concrete. This next step is to choose a competent site contractor. Again, one familiar with precast concrete. There's a difference between in situ concrete on site and precast concrete on site. That contractor needs a construction manager and preferably a temporary works designer. They can often subcontract out the temporary works, but temporary works is vitally important to precast concrete construction, as it is to most construction, but it's on the critical path for precast concrete construction. The next, choose a competent precast contractor. And as I said, you need one with a technical team able to produce shop drawings. Now, if you've got a precast contractor, and there are lots of precast contractors in New Zealand, not all of them have a technical team. They don't have engineers or they don't have technical staff who can produce shop drawings, which is really a problem. I suggest you pick a different precast contractor in that case. One of the things that they should do is pick up on some of the mistakes you may have put on, or some of the difficulties that you've put in your design that are just not practical to build. And get them together at the earliest opportunity as well. So bash around with some ideas of the concept design of the building. It's much easier to change the elements of a building in the design stage than when you're building it. So an example construction sequence, this is for a precast concrete panel. So you put the panel up, prop it, align it and level it, dry pack and grout the base, grout the Drossbachs or the grout sleeves, and whichever is the case, and then add the next level. It seems obvious really, but it's amazing how many people don't put it in that order and start building the next level before they've grouted the level below. Ideally, the sequence of deliveries should allow you to place those panels directly from the truck, so you can avoid the double handling that's associated with lifting off and storage on site. However, most precasters want to deliver several panels at the same time on one truck. Ideally, complete the sign-off of the shop drawings before construction begins. Shop drawings are a pain in the bottom, basically, and they take far more time to draw and to check, review and prove than anybody ever allows for. So part two, the secrets of successful precast construction follow other aspects of successful construction. Keep it simple. So that was lesson number one in seminar number one, the KISS principle. Keep it simple, stupid. If you add complexity to your project, you are not being clever. You are adding costs and you're adding delays to your project. Standardize. The whole point of precast concrete construction is you make the same panels over and over again, and you use them over and over again. And that was the secret of Henry Ford's success. So that should be the secret of anybody doing precast concrete. Allow the panels to be interchangeable so that if you're not ready to use one panel in one place, then it can be used somewhere else. If every panel on your job is unique, then if it goes wrong, it then gets scrapped. And repeat and repeat, repeat. So you use the same panels over and over again across the floor and then up the building as well, level by level. Tolerance, allow lots of it, and it's a big issue, is tolerance on site. On a construction site, you're unlikely to get anything built, I'd say, to the nearest inch, 25 millimeters. You really need to allow at least 25 millimeters, and I mean plus or minus 25 millimeter tolerance. And grout sleeves don't allow that at all. It's ±8. And the chances of getting starter bars cast in to in situ concrete to ±8 millimeters are pretty much well, close to zero, sadly, which means a lot of retrofit work. Construction sequence is very important, and make it easy to build. The more difficult it is to build, the slower it will take, or the longer it will take to build. And manage the construction process. You need to have a really good construction manager. That's not the designer. It's not necessarily the precaster. It's somebody on site full time who is managing the process. So they hint it's all about timing, and we say it's not rocket science. So what's so clever about rocket science? The really clever thing about rocket science is the timing. It's all about timing. So before construction begins on site, you need to get the council on board. So is your resource consent still valid? What are the conditions that have been applied or attached to that resource consent? Is the building consent still valid? Now, building consents in Auckland are only valid for a year, and if you don't start building within the year, you need to reapply and extend your building consent. Yes, really. So invite the council along before you start building to notify them that you are building. Get the whole design and construction team together and talk before you start building. It's basically the start of the project on site. You need to check that all the design documents have been delivered and approved. Have they been coordinated and integrated? So the trouble is, we as structural engineers want to design concrete and steel. There's other engineers who are providing the services, and they all want to put holes in your concrete. And some of those holes can be rather large. You will need to allow for those holes and put them on your structural drawings, because if you're not on the structural drawings, they will get missed. And get the shop drawings done and signed off as soon as you can, as soon as you begin construction, basically, preferably before you need the panels. Get the temporary works designed and signed off as well. All of this before the construction really begins. And plan the site. One of the aspects, of course, you're entirely dependent on a crane, and you plan the site to have a crane. Is it going to be a static permanent crane? Is it going to be a mobile crane? If so, what's the routes in and out? If it's a congested site, how do you get the crane erected, and then how do you get the crane dismantled as well? I've given a plan of the construction process. So as a template here, you don't have to look at it, but basically it's all the aspects of all the elements of your construction listed down on the left hand side. Who's going to supply it? What equipment do you need? Who's a subcontractor? And it's dates. When is it delivered? And when's the start and end date of these activities? The checks, all of these things need to be checked. So you have setting out lines and levels, the delivery condition. If the panel is damaged when it arrives, it really should be rejected rather than patched up. And have you completed it? So all the components of one level completed before you go on to the next. Some of these you want the engineer, the person doing the PS4, apart from your CPD person, to check each of these things. And then you realize you're not exactly a rocket scientist. Okay, so the two main references for this component were the structural precast concrete in buildings, and this is available as a free download. It's a bit old now, and some of the details in it I would rather suspect, but it gives you a general overview of the precast concrete business and the techniques you may need to use and consider. On the other hand, there are lots and lots of resources from Reed, and I can't imagine doing a precast concrete building without getting Reed involved in some component. And there's this concrete lifting design manual, which is fairly comprehensive, but there's also other manuals available from them, which are worth looking at as well.